At the end of the last lecture, we were talking about lists and recursion. So we were looking at this other variation of the jump it problem. So you've got a board, which is just a list of integer numbers. You start at the left-hand side. You want to reach the right-hand side of the board. The number that's on a square, that's the number of squares that you can move left or right. So starting at the 2, I can go to the 4, for example. Right? So here, to solve this particular board, starting at the 2, I can go to the 4. I can take 4 steps to go to the 1. Now I can go to the 2 or the 6, so we'll go to the 6. I can't take 6 steps to the right because I fall off the board, so I have to go left. Right? I'm at 3. I can't take 3 steps to the left, so I have to go right, and that solves the problem. So we've already looked at this problem. Now, like the jump it problem we studied on Monday, the number of steps or the number of possible solutions is exponential. It's 2 to the some exponent, because at each step you're allowed to take one of 2 possible moves. Sorry, up to 2 possible moves, right? So solving this problem using a regular old loop or loops it's not so obvious how you would do it, but it turns out using recursion, you can write a fairly straightforward solution. So to use recursion, you need some base cases. It turns out there are some simple base cases for this problem. But also like recursion, you have to shrink or reduce the size of the problem every time you make a recursive call. Otherwise, you cannot guarantee that your recursive solution will actually reach a solution. In this problem, it's not exactly obvious how the board gets smaller. So in jump it, once you move to the right, you never have to consider the squares to the left anymore. So the board clearly gets smaller. In this problem, because you can move left or right, it's actually not immediately obvious why the board gets smaller, right? But the board gets smaller because every time you step on a square, you don't want to return back to that square. Otherwise, you end up in a cycle, which means that a solution might not exist. Right? So to indicate that you've been on a square before, we're going to modify the board. So when we step on a square, I'm going to set the value of that square to a negative value to indicate we've been on that square before. The recursive cases are pretty straightforward. Right? So recursive case number 1, can you move left? Right? So if I'm on a square and it's got some value on it, right, I can move left as long as I don't fall off the board. Right? That's easy to check for. Right? If you can move left, then you want to answer the question, can I solve the board if I move to the left? Right? So if I move to the left-hand square, can I solve the board from this square? Right? And we're just going to use recursion to answer that question, because the method that we're writing is supposed to solve the problem of if I'm on a square on the board, can I solve the board? Similarly, can you move right without falling off the board? Right. So if you're on some square here, you can move right as long as you don't go past the end of the board. Again, that's easy to check for. Right. If you can move right, then move right and see if you can solve the board. So we're going to use recursion to solve that problem as well. Right. So there's 2 recursive calls for every. There's potentially 2 recursive calls in our method. Right. So here's our method. The method's called isSolvable. It's going to return true. If the board is solvable, it will return false if it's not solvable. Now, it will return solvable. It will return true if it's solvable when you're on that location of the board. Right. So when you call this method for the first time, you're going to pass in 0 to indicate that you're at the left-hand side of the board. There's our board, right? So it's just a list of integer values. Okay, so I'm going to ignore the base cases for now, but later on we're going to insert them right there, right? So when I enter the method, I'm on that location of the board, right? So that location tells me how many squares to move left or right. So I need that value. Right? So the value is the number of squares to move left or right. Right now, when I enter the method, I'm on that square. So I don't want to return back to that square in this solution. So I'm going to modify the board, putting in a -1 on that location. Now, back here, the contract for our method says that the method's not going to modify the board. Right? Here, I'm modifying the board. So this is fine as long as I undo this before I return from this method. Right? So I have to remember to unset the board before I return. Right? In other words, I have to set the board location at that index back to that value. Right? Which is one of the reasons why I'm storing value as a variable here. Okay, so we've got that. Now, our first recursive case shown in the gray rectangle. Right? So the question is can I move left? Right? And I want to know does a solution exist if I move left? Right? So when left will be true if moving left leads to a solution. Right? So can I move left? Well, I'm on that location of the board. Right? That's how many squares I have to move. So index minus value, that's the index of the square if I move left. Right? Now that index has to be positive or 0 in Java, right? So I want to check, is that new index, or if that is that left-hand index, is that greater than or equal to 0? If it is, I can move left, right? So I want to know, is the board solvable if I move to the left? Right? And I just pass in the board. Right? Now notice when I pass in the board, when I call the method recursively and pass in this board, that board's been modified to indicate that the current square that I'm on has been visited before. So when you make the recursive call, this recursive call will not consider a solution where you're currently, that takes you back to this current square. So that's our recursive call for moving left. Now you're going to do the same thing for moving right. Right? I want to know, can I move to the right? Right? Do I win if I move to the right? Well, what's the index to the right? It's just index plus value. When is that a valid index? When it's less than the size of the board. Right? So if that's all true, then I can move right. So I'm just going to try going right and see if the board is solvable. Right? So is the board solvable if I move to the square to the right? And then what's the answer? Well, if that's true, or if that's true, then I know that the board is solvable. Right? If they're both false, I know the board's not solvable. So answer is, right? So what's the answer? Well, if when left is true or if when right is true, I return true. If they're both false, we return false. Right? So I can use or here. And now I have to remember to unset the board before returning. So here's where I unset the board. Set back the board at the current square back to its original value. So as far as the caller is concerned, their board never changed, even though we actually did change it in the method. And there's the recursive part of the method. Now, if you're paying attention, you know that right here, oh, sorry, never mind. I was going to say something. Never mind, that's fine. Oh, wait, yes, right here. If when left is true at this location here, you can just return true at this point here. So there's a small optimization that you can make on this line here. Right? So if when left is true, return true, because you know that you can win by moving to the left. Right? It doesn't matter if you reverse the order of these two recursive calls. Right? You can try winning, going to the right first, or you can try going to the left first. It doesn't matter. Either way, you will eventually find a solution. Okay, so our recursive method's almost complete. We just have to figure out what the base cases are. Now remember, the base cases, those are the cases where you know the answer, right? So when do I know that the answer is false, right? I know the answer is false if you reach a square whose value is -1, right? Because that means you've landed on a square that you've been to before, right? So you don't want to consider that solution. So you can return false if you see that, if you reach that case. The other time we know that the solution has been found is when you've reached the last square, right? you know the answer is definitely true if you reach the last square of the board, right? So then you know the board is solvable. So those are your two base cases. Right? When you're writing these recursive methods, the temptation is to do things like, right? Check, can I move left? Right? And if I move left, do I not land on a square that I've been to before? Right? So that's the temptation, right? Because you don't want to move to a square that you've been to before, right? When you're writing recursive method, you should try to avoid complicating your conditions where you make the recursive call, right? You should simply rely on the base cases, catching situations where you know that the answer, one way or another, right? So if you put in this base case here, right, where you land on a square whose value is -1, you don't have to worry about putting in any logic here to make sure you don't step on a square whose value is -1. Right, just rely on the base cases to take care of that for you. Okay, so the base cases are easy to code, right? You reach the square whose value is -1. Well, right? So if board get index is less than 0, you can return false, right? Otherwise, if you reach the right-hand side of the board, so you reach the right-hand side of the board when that index is equal to the board size -1, right? That's the largest index you can have for that board. And then you return true, and that's it. Right? So there's how you solve that particular problem using recursion. And this is another example of a problem where the recursive solution is easier to write, assuming you're comfortable with recursion, than it is to try to come up with an iterative version of the solution. I guess we're looking at one more recursive method. So I assume you've done sorting at some point in time in one of your previous courses. I assume that they taught you how to sort a list or an array of some kind. Maybe they taught you what selection sort was, maybe they didn't. I'm going to show you a recursive version of selection sort. All right. So I want to first write a method that recursively moves the smallest element to the front of a list. And I want to do this recursion. Now you can obviously you can do this with iteration. Right? So you can easily loop over a list to find the smallest element and then move it without using recursion. But doing this with recursion is interesting because it's really strange when you see it the first time. So I want to move the smallest element in the list to the front of the list using recursion. So here's a picture of what's going to happen. There's my original list, right? Now, how do I recursively move the smallest element in that list to the front? So the smallest element's the 0, which I can see, right? So I want to move that 0 to the front somehow, right? But I want to do so using recursion, right? So in a recursive solution, you always want to shrink the size of the problem every time you make a recursive call, right? So suppose I have my recursive method already written, right? One way to solve this problem is to look at this sublist here, right? So ignore the first element of the list. You can also ignore the last element of the list. It doesn't matter. No, so to move to the front, you want to ignore the first element, right? I want to recursively move the smallest element in this sublist to the front of the sublist. Right? So in other words, I want to move the 0 to here, right? So I can do that, right? So I have my recursive method. I'm just going to assume it's going to work, right? So after calling that recursive method, I know that eventually the 0 is going to be here. I have no idea what the rest of the list is going to look like at this point in time. But I know for sure the 0 is going to be here, right? Now that the 0 is in the second location of the original list, right? All I have to do is compare these two elements, right? Whichever is the smaller element, I'm going to move that element to the front of the list, right? So in this example, 0 is smaller than 8, so I just switch them, right? And swapping them, that I don't need recursion, right? I just swap these two elements. I'm done, right? So recursively move the smallest element of the sublist to the front of the sublist, and then swap if you have to. Okay? That's what our recursive method's going to look like. So here's min to front. Ignore the base cases for now, right? Step one is I'm going to recursively move the smallest element in the sublist, not including the first element of the original list, to the front of the sublist. I'm going to call min to front recursively. And I'm going to pass in the sublist that does not include the first element of the list. So this is the sublist starting at element, the second element of the original list. When this method is done, I know that our original list T is going to have its first element, its original first element at the front of the list, and the smallest element in the rest of the list sitting in the second element. Right. So now I do the swap if I have to. Get the first and second elements using get. Right. So get 0, get 1, first and second element. If the second element is smaller than the first, I just switch them. Right. So if they're smaller, I set the first element of the list to the second element. I set the second element of the list to the first element. And that, so there's your recursive part of moving an element, moving the smallest element to the front of the list. Right. Now, what about our recursive cases? So in our recursive cases, right, the list is going to get smaller and smaller and smaller. So to move the smallest element in this sublist to the front of the sublist, I'm going to recursively call the method. Right. So I'm going to try to find the smallest element in that sublist, right, and then that sublist, right, and then that sublist, and then this one, until I get to a list of size 2, right? Because when I get to a list of size 2 or 1, you can do either, right? I get to a list of size 1, for example, right? Then I know there's nothing to do, right? The smallest element in the list of size 1 is the element that's in the list, right? So I can use that as a base case. So if the size of my list is less than 2, just return the smallest element's already at the front. Writing the base case like this is nice because it also works if the list is empty. Right? So if I pass in an empty list T, right, the size of the empty list is 0, so I simply return. Right? There's nothing to do. There's nothing to do if the list is empty because there is no smallest element. Right? The list is size 1. Again, there's nothing to do because the smallest element is already at the front. Right? Otherwise, use recursion. And that's it. So that moves the smallest element to the front. Now, what happens if I repeat this process? Right. So I've moved the 0 to the front of my list by using min to front. Right. Now, if I call min to front again on the sublist, what's that going to do? Well, that's going to move the smallest element in the rest of the list to the front. So I'm going to get the 1 in the front. Right. And now I'm going to do the same thing. So now call min to front on the rest of the list. Right. So the 2 now comes to the front of that sublist. Right. So the 2 moves to the front of that sublist. And now I call min to front on the rest of the list. Right. There's the 3. There's the 4, 5, 6, 7, 8. Right. So when you reach a list of size 2, I'm going to call min to front one more time. Right. And now I've got a sorted list. So this is the selection sort algorithm. If they taught you this algorithm, they almost certainly didn't teach you this way to do it. They would have used a loop to do this, 2 nested loops to do this. Right. But this is the selection sort algorithm. So selection sort moves the smallest element to the front of the list at each step. Right. After moving the smallest element to the front, it proceeds to the second or to the next element in the list. Right. And so on and so on and so forth. But the selection sort algorithm written using recursion just looks like that, which is kind of cool because if they did teach you selection sort, you would have seen a nested loop where you had to do a bunch of bookkeeping. Here, I just call min to front and then sort the rest of the list. Right, so that's all that's happening here, right? So I move the smallest element to the front of the list, and then I sort the rest of the list. And you do that as long as the list is bigger than size 1. Right? And there's selection sort written recursively. So that's another example of using recursion on lists. Right? So the sublist method turns out to be very useful if you're thinking about problems in a recursive way. All right. I'm going to ignore this slide. This is deals with the computational complexity. It's for the purposes of this course, it's not important. All right. So that's the end of the list lecture. So the important methods in the list class, they're get, set, remove, size, and is empty. There are other methods in the class which are occasionally useful, but the main ones that you tend to use are get, set, and remove. Right. If you have, there are more specialized uses of lists where you need to do things at the front or the back of the list. So in those cases, you probably want to use a linked list because doing things at the front of an array-based list is inefficient. But we'll talk more about that when we look at the implementation of array and linked lists. All right, so that's the end of the list lecture. I want to do this. I want to do sets now. Where's my set lecture? All right, so as C programmers, you probably, well, you might have seen a set implementation in your data structures course. You may not have. I don't know if you did or not. But in languages like Java and Python, sets turn out to be somewhat common. And I'll explain why that's the case in a second. So sets model the mathematical definition of a set. Right? So a set is a collection of unique elements. So that's the mathematical definition. Right? In other words, there are no two elements in a set that are equal to one another. And so when in a programming language, sets are used to make sure that you have a unique collection of elements, right? No duplicates. So common uses of sets include membership testing. So this means, is there an element in the set? Right? So is there some element that's equal to some element in the set, right? Now lists also have this, right? So lists have the contains method. Right? So is an element, does this list have a particular element? Right? But in lists, that membership test is expensive, right? Has complexity big O of n, right? Because you have to search the entire list. It turns out that sets, you can answer this question much faster. So if you need to know, does this element exist in a collection, then it turns out using a set is usually faster than using a list, unless the list is sorted. If you have a list and you want to remove duplicates from that list, then sets are handy. You just take the list and put it into a set, and the set will take care of removing all your duplicates. So removing duplicates turns out to be quite common in computing applications. If you actually are modeling a mathematical problem that involves sets, you want to compute the intersection, the union, or the difference, then the Java sets let you do that. Now, the reason, probably the bigger reason sets are commonly used in Java and Python, well, Java, sorry, is that there's something called a map, which uses a set. So in order to use a map, you need to know how to use a set. And maps turn out to be really useful as well. Sets are odd if you're used to working with lists, because when you work with lists, you're used to saying get element I, set element I, right? Or do something with element I of the list, right? You're used to being able to randomly access elements of a list, right? There is no indexing in a list, in a set, right? So you can't index, you can't get an arbitrary element from a set, right? You can ask if the set has a particular element, right? But there's no numbering or labeling of elements in a set. Okay, so there is something called, there is a data type. There's an abstract data type called set, right? And that abstract data type models the mathematical abstraction, the mathematical definition of a set. They don't normally, it's not common, or not, I don't know if that's true. Often you don't learn about sets in your data in a typical data structures course. So if you haven't seen this data type before, don't worry about it. In Java, you can choose between several different kinds of sets, but normally you choose between two. So there's something called a hash set. If you studied hash tables in your data structures course, then that's how a hash set is implemented. If you haven't seen a hash table, again, don't worry about it. And there's something called a tree set. So a tree set is a set that sorts its elements. So if you have an application where you want your elements to be in sorted order, then you can consider using a tree set. Somewhere, do I point this out? Oh, I don't point this out. Okay. Normally you choose hash set. So if you have, if there's no reason to sort the set, then you would choose hash set because hash set is faster than tree set. Hash set is very fast. I think later on I'll explain how fast it is. Okay, like lists, sets in Java are generic, so they can hold elements. You can create a set to hold elements of a specific type, right? Like lists, you're going to use the diamond operator to specify what is the element type, right? And also like lists, you can't make a set of primitive elements. So you have to use the wrapper classes. If you want a list of int, you have to use big I integer instead, right? And like lists, right? When you create a set, so here I'm making a hash set. You specify the generic type here. You can, if you want to, specify the generic type on the right-hand side when you call the constructor, but you don't have to, right? Because the compiler can infer the type from the left-hand side. So when you call the constructor, you can just write that, right? Assuming you have a variable of the right type on the left-hand side. We've talked about this before, so I'm just going to skip over the slide. Okay, so what can a set do? So a set does, so things like a hash set can do, or have a smaller number of methods than lists. So you can ask, is a set empty, right? You can ask for the size of a set. Right? I can add an element to the set using the add method, right? Now, when you add an element to a hash set, you have no idea where that element's going to be put into the set, right? If you add it to a tree set, you know that the element will be added so that it's in sorted, so that all of the elements are in sorted order, right? But if it's a hash set, that thing can go anywhere into the set, right? And you don't know where it's going to go. Contains is the method that you use to ask, does the set contain an element equal to that? And remove is the method that you use to remove that element equal to that. If you want to copy a set, you just use the constructor, right? So if I have a set t, then I can make a copy of t just by passing t to one of the set constructors, right? So if you have a hash set t, you can make a tree set of the elements in t by writing tree set string u equals new tree set t. And that'll give you a sorted set of the elements. Okay, now normally you use hash set. If you have no reason to prefer a sorted set, then you would use hash set. The reason you would use hash set is because it's extremely fast in its main operations. Right? To add, remove, or ask the hash set if it contains an element, it has expected O1 complexity. Right? In other words, constant time, which is what you aim for when you make a collection, when you design a data structure for collections, right? You want it to be as fast as possible. Hash set is as fast as possible for these in terms of its computational complexity. Now, the disadvantage to using a hash set is you don't know the order of the elements in the set, right? So if you read the documentation for the class, it says it makes no guarantees as to the iteration order of the set. So in other words, the elements can be anywhere in the set, right? It does not even guarantee that the order will remain constant over time. So if you have a hash set and you add something to it, then the order of the elements can change. That would be unusual, but it can change. right? If you start to remove stuff from the hash set, then, well, sorry, if you add stuff to the hash set, then there's no guarantee that the order of the element stays the same. In a tree set, they're also fast. So tree set's also very fast. Its add, remove, and contains methods have complexity big O of log n, right? Which is also very fast, especially compared to a list, to an array-based list anyway, right? If you remove something from an array-based list, that has O(n) complexity. Contains has O(n) complexity for an array-based list. Inserting into a list, so into the front or the middle of a list, also has O(n) complexity. Right, so the sets are faster than lists. Now, in a tree set, the elements are ordered by their natural ordering. So in other words, the elements are sorted. Right, now, in order for this to work, your elements have to be sortable. Right, so your elements are sortable if they have a compare to method. Right, so remember when we talked about strings, right? We saw that string had a method called compare to that lets you compare two strings for their dictionary order. Right? The way that's expressed in Java is that it implements something called an interface, which we'll look at a little bit later in the course. Right? So for now, if you want to use a tree set, just remember that whatever you put into the set, it has to have a compare to method. There is a third kind of set that is occasionally useful, and it's the kind of set for people that really want a list. That's basically what it is. So if there's something called a linked hash set, right? So a linked hash set guarantees that the order of the elements is identical to the order in which you put things into the set. Right, so if you make a linked hash set and then you add A, then B, then C, if you loop over the set, you get back A, then B, then C. Right, so it maintains it maintains elements in their insertion order. Now the way it does that is it essentially internally it has another more or less has a list inside of it. Right, so that means that your set actually takes up twice the amount of memory as a hash set, for example, right? Roughly twice the amount of memory, right? It needs additional memory that's proportional to the number of elements in the set. But it trades off memory for computational complexity. It's similar to a hash set in that add, remove, and contains is very fast, right? So it has constant time complexity. Slightly slower than a hash set, because it needs to do extra work to remember what the iteration order is. Okay. Now, because you don't have any indexing in a hash set, in a set, if you want to loop over the elements in the set, the only way you can do that is using a for each loop. If you're reading the notebooks, you know that you can use an iterator as well, right? So you can make an object called an iterator that knows how to loop over the elements of the set. I'm not going to talk about that in this lecture. So if you have a set called T, and it's a set of strings, then you can loop over the elements in the set using a for each loop, right? So for each string S in T, right, you can do something with element S inside the loop. So that's how you loop over the elements in a set. Okay, so you use a set when you want to ensure that the elements in your collection are unique, right? That's the purpose of a set. So if I have a list and I want to find all of the elements that are duplicates, right? Then I can use a set to remove the duplicates, right? So I can find the unique elements. It's also possible to find the duplicated elements, right? So suppose I have a list, right? And that list is just so it's a list of strings, right? And the strings in the list, those are just like user account names, right? So for example, right here, Right, so here I've got a little class called set examples. It's got a little main method that has all the examples in the lecture slides. So I have a list here. Right, so it's a list of strings. I'm just going to add a bunch of accounts, a bunch of user accounts to my list. Right, so here I add 6, I think, accounts. Right, and 2 of the accounts are duplicated. Right, so SP Kuma shows up twice, and D Parrot shows up twice. Right. So if I print out that list, right, I'm going to, well, let's run the program and see what we get. Right, so when I print out the list, I get that list there. Right, and you can clearly see that there are duplicated elements in the list. Now, if I take that list and I give it to the constructor of a hash set, right, then what the constructor will take each element of the list and add it to the hash set. Right, so when it finds the duplicate elements, it won't add those to the set. Right? So if I print out the hash set, it looks like that. So you can see that it has the elements HP 1304, dparrot, SP Kuma, and Arian 98. Right, so those are the unique elements that are in the list. Right, now notice that the order of the elements is different than the order of the elements of the list. Right, and that's because hash set makes no guarantees of the ordering of the elements. Okay. Now, if I make a tree set with the same list of names and then print the tree set, right, you end up with a set that has the same elements as the hash set, but they're in a different order, right? And in particular, they're in sorted order, right? So these are sorted alphabetically. With a linked hash set, again, you've got a list of 4 elements, but the order of the elements matches the order of the list, right? So you add that element to the set, then you add that element to the set, then you add that element to the set, and then you add that element to the set, right? The 2 duplicate elements, they don't get added to the set, and it doesn't change the order of the existing elements in the set. Right? So that's the difference between the 3 types of sets. So those are those 3 examples right there. All right, so that lets me get the unique elements. Now, how do I find the duplicated elements? Right? So if you want to find the duplicated elements, you need a pair of sets. Right? So I need 2 sets. So the way this works is you make one set for the unique elements, and then you make a second set for the duplicated elements. Right? Now I'm going to loop over my list. I'm going to loop over the list, and I'm going to add each account to my set of unique account names. Right? So I'm going to use the add method. I'm going to call the add method for the unique account set. I'm going to try to add that user account name. Right? Now, the way the add method works for sets, it returns true if that element is not in the set, and then it adds that element to the set. If this element's already in the set, then the method returns false and does not add the element to the set. So this says if that account is not in the set of unique account names, right? Then if that account is already in that set of account names, right? And add that account to the set of duplicated accounts. Right? The reason you use a second set here is because if that account is duplicated many times in the original list, you don't want it to show up many times in this collection here. Right? So if you use a set here instead of a list, then you're guaranteed to get a unique set of duplicated accounts. That example is right here. I'm just commenting out all the following examples as we go. So if we run that, you can see here that your duplicated accounts, it correctly finds the 2 duplicated accounts. Okay, so this is a picture of how that example works. Right. So there's my list of account names. Right. I'm going to loop over this list and add them. Try to add them to this set here, to the set of unique accounts. Right. So SB Kuma goes in, right, because it's not there already. dparrot goes in, HP goes in, Arian goes in. Now, when I try to add SB Kuma again, it's already in the set of unique accounts. Right. So add now returns false, right, which triggers the the body of the if statement to run. So SP Kuma goes into the duplicated account set. Right. You try to add dparrot. Well, dparrot's already in the set of unique accounts, so they go into the duplicated accounts. Right. So that's a picture of how that example works. Okay, so the set union operation is the same thing as the mathematical union operation for sets, right? So the union of two sets is just the elements that are in either one of the two sets. Right. So I suppose I have a set containing the accounts of students who completed assignment 1, and a set of students containing the accounts of and a second set containing the accounts of students who completed assignment 2. Right. I want to know who are all the students that completed either assignment. Right. So if you have a problem like that, you use the union. Right. So set 1, that's my set of accounts of students who completed assignment 1, and S2. That's my set of accounts of students who completed assignment 2, right? I can find all the students who completed either assignment by using the add all method. So S1.addAll S2, right? Basically what that does is it takes every element in S2 and adds it to S1, right? Now, why is that the union? Because any duplicate elements in any element that's in S2 that's also in S1 will not be added to S1. Everything that's in S2 that's not in S1 gets added to S1, right? So S1 becomes the union of the two sets. So I can make a set called either assignment. I can add all the elements of set 1, right, to that set. Right, so that's all the students who completed assignment 1. And now I just add all the students who completed assignment 2. Yeah, I have a picture of that too. Right, so there's the students who completed assignment 1, students who completed assignment 2. There's my set called either assignment, right? So we put all of these students into here. Right, now I'm just going to loop over the elements in this list, in this set, and try to add them to here. Right, so add all does the looping for me. Right, is SP Kuma here? It's already here, so they don't get added. Is dparrot here? Yep, they don't get added. QZ is not here, right, in the set, so QZ gets added to the set. And devc is not in the set, so it gets added to that set. Right, so either assignment becomes the union of those two sets. And if you want to, you can we can run that example here. Oops, sorry. Right, so here's set 1, right? So I'm going to use add to add those students. Right, there's set 2. Right, again, I'm going to use add to add those students. Right, and then finally, I'm going to find the union of those two sets, right, by using add all here. Okay, so if you run that, oops, sorry, if you run, I run that, you should get you get the set that's shown on the slide. Okay, now what about the intersection of two sets? So the intersection of two sets, that's the exact same thing as the mathematical definition of the intersection, right? So it's the set of if you intersect two sets, then the intersection is the set containing the elements that are in both set 1 and set 2. So if I want to know the students who completed both assignments, you use the intersection. So the intersection method is called retain all. So S1 retain all S2, right? So that transforms S1 into the intersection of S1 and S2, right? So what that means is every element in S2, right? We're going to check, is it in S1, right? If it's in S1, we're going to keep it. Otherwise, right? Sorry, for every element in S1, we're going to check, is it in S2, right? If the element is not in if the element is in S1 but not S2, then we remove the element from S1. So that's how this method works. Okay, so again, students who completed assignment 1, students who completed assignment 2, students who completed both assignments. So we're just going to take these students, put them in here, right? And I do that using the constructor. Right. Now, retain all is going to loop over the elements here. Actually, it's going to loop over the elements here and check, are they in here? Right. So after calling retain all, it only keeps the first 2 students. Right. So it's back. So is SP Kuma in here? The answer is yes. So we keep them. Right. Is D parrot here? The answer is yes. So we keep them. HP 1304 here. The answer is no. So they go out. Right. And is area 98 up here? The answer is no. So they go out, which produces that set there. Right. And again, we can run that example in Eclipse. And you get the answer that's on the slide. Okay, last example is set difference. So the difference between 2 sets removes. So S1, the difference of S1 and S2 removes all the elements that are in S2 from S1. So if I want to find the set of students who completed only assignment 1, right, I take the difference of S1 and S2. Right, this is the same thing as the mathematical definition of the set difference. Here's our picture, right? Students who completed assignment 1, students who completed assignment 2. I want to know who completed assignment 1, so I put all the students who completed assignment 1 here. Right, now, when you call remove all, it is remove all, right? Yeah, when you call remove all, we're going to loop over this set, right? Every element that's in this set that's also in S2, we're going to remove them, right? So SP Kuma is here, so they're going to go out, right? D parrot is here, so they're going to go out, right? Elements are not in here, so they'll stay, right? And you end up with HP 1304 and area 98. And the last example. Produces, oh, okay. Produces the same answer that's on the lecture slide. Okay, so those are the operations that are common to all of the set types in Java. Now, tree set, oh, sorry, I should stop there. It's 20 after the hour. Anybody have any questions about the recursion problems for lists or sets?
Sorry, could we clarify? Oh,
go ahead.
Could we clarify something about the assignment that's due today?
Oh, sure. Yeah, that's fine.
So at the bottom of the assignment, we were asked to create a degree method at the very end, and there weren't instructions stating whether we should like call it within the main function or what values of I we should put in to just show that it works.
No, so we're going to test it separately. So if it's in your class, we can still test it. So I can write a separate program to call your degree method to make sure that it works. If you want to, you can call it yourself from your main method. That would be fun if you want to check. Or you can write another class that has a main method.
Okay, so all we need is that method, and we should just leave anything out of the main function.
Yeah.
Okay.
So one of the so that actually I've been asked that question several times now. So one of the things that you have to get used to when you're writing software is when you're writing software, you're not always writing it just for yourself, right? You're writing it for a lot of the time you end up writing it for other people. So one of the methods that you might want to, someone who's using your sandpile class might want to know is what is the degree of a cell, right? So it's useful to have that method. Now, just because you're not using it in your own program doesn't mean that it's also not useful. So there's sort of this transition that you have to make where you're writing functions or methods that aren't immediately useful to you, but might be useful to you might be useful to you or someone else in the future. Any other questions? All right. If you haven't noticed, I did send out a Teams invite to the to office hours. So I now have set office hours. They're also on OnQ if you haven't seen them, and there's a link on the OnQ homepage for the course to the Teams meetings. All right, so you can find my office hours now. Any other questions?
Yeah. Can I get you to take a look at my IDE issue again, possibly?
Oh yeah, you want to do that now?
Yeah.
Sure. Do that now.
Everybody
else, I guess we're done, unless you have some questions.